In this video, we're going to start taking a look at some concepts from calculus. Namely, we're going to look at the ideas of limits and continuity. We're going to analyze these things from a real analysis perspective. So we'll build them up. We'll think about what those definitions are and how that looks, building it really from the ground up. So let's first define a limit. So let f be this function that maps from a domain D into a codomain of the real numbers. Let C be an accumulation point of that domain. We say that a real number L, this is a limit of f at C, denoted in this way, right? So that parallels the same notation that we had back in calculus, but the L is a limit of f at C if for every single choice of epsilon greater than 0, there exists a delta greater than 0, such that the distance between our function and the limit L is less than epsilon whenever our value of x is in the domain, and that value of x, the distance between the value of x and c is less than delta but greater than 0, right? And so what that's telling us about that choice of x is that the choice of x is in a neighborhood about c with radius delta. But more than that, it's saying, because it says it's strictly greater than 0, it's saying that it's in a deleted neighborhood, right? So we aren't taking the point, we're not allowing our value of x to be equal to c itself. And we've also required that that value of x is in the domain. So x is in that intersection, is part of that deleted neighborhood, and is also part of that domain. Right. We can take a look at this idea. We can think about what that looks like graphically. I've started to draw a little bit of that here. And so as we take a look at that, if we were to say we want our function to be within epsilon units of L, what that tells us is we kind of have this space. We want to be within epsilon units of L. So this is L plus epsilon. This is L minus epsilon. And we ask ourselves, what requirements do we need to put on x in relation to c in order to guarantee that every function value in this range is going to for sure be less than epsilon, right? And so when we do that, we are going to say, for every epsilon, there exists this value of delta. So we're going to come up with a value of delta. That value of delta is often built on the choice of epsilon. Right. And so we're going to say, like, what if we go delta units away from C, right? So if we go delta units above C and delta units below C. We want to make sure that whenever we have values of x that have a horizontal distance away from C that is less than delta, that whenever we have an x in this range, our outputs, the function values, are going to for sure be within this range. Now, when you look at this particular graph, you might say, well, maybe we kind of get it, like, why didn't we choose it way down here? Well, if we chose our delta in this way, so if this was our delta, then when we went above delta that many units, then we would have some points that have function values that are more than epsilon units away from L, right? And so we don't want to choose our value of delta in that way. We have to be careful about how we choose the value of delta. It may end up being a little bit more restrictive on one side and not allow values to be quite as far away from that limit, but we still are guaranteeing that it's within epsilon units of L on either side. Right? And so here we think about whenever our horizontal distance, whenever this horizontal distance down here, whenever we're within delta units of c, then we are sure that we are going to be less than epsilon units away from L in a vertical distance. Right? And so that's how we actually formally define a limit. So L is a limit of f at c, denoted in this way, if for every choice of epsilon there exists a delta such that the distance between the function evaluated at some x value and that value L is less than epsilon whenever the x value is an allowable value in the domain and the distance between the x value and the point that we're taking the limit at is that distance between that x value and that point is less than delta. All right, in the next video, we will take a look at an example. We'll see you there.